Okay, now for the experimental part, we have a tube that has a cap that we're going to remove for now, and there is a narrow diameter tube that will fit inside the other tube, and we're going to use this to vary the length. Okay, so based on the discussion about waves, what we're going to do is we're going to take two different tuning forks. Okay, both tuning forks they're close to each other. One is 480 hertz, and it's actually a B note, and then we have a C note of 512 hertz. All right, so these two tuning forks we're going to strike and then use them to try to find resonance. So we're going to allow the sound waves to oscillate through these pipe, and we'll try to find the length at which we get resonance for this. Okay, so I'm going to take my meter stick, all right, and I am going to actually turn this one around so that 0 is at this end. So I can make a nice easy measurement. Okay, so first I'm going to hit this end. So pretty close around there. Let's do it one more time. So for this measurement, see that I'm exactly 35.5 centimeters. Okay, so I'm going to write that down for my length of the tube, and for this will be for tuning fork 1, so I'm going to make note that this is going to be the B, or the 480 hertz. So I'll write 480 into the table. Then I'm also going to write down the length that I've got. Now normally you would do these different trials with a lab partner. I'm doing this all by myself. Not many people on campus right now, so I'm just going to do 3 trials by myself using my ears. So this first trial I see 35.5, so that would be 0.355 meters. Okay, hopefully you'll be able to read my handwriting here. All right, so let's do it again. Okay. In this case, I am exactly, again, 35.5. So it's 0.355. Do it one time. I'm going to call that one good. And this time, okay, a little different. I'm at 35.7. Okay, so your job is going to be to find the average length of these. Okay, then I've already given you the frequency, so you'll calculate the wavelength. Now remember, on this open-ended pipe, the resonance that we can find is only going to be half of the total wavelength. So you take this length and you double it, okay? We've made this pipe so that it's a little bit too long to get anything less than that, and it's also too short to get to the next resonance point, okay? So I am now going to switch over from the 480B. We're going to go to the C, okay? So the C down here is going to be 512. All right, and I'll start taking the trials for this one. So I'm trying to find when it's the loudest. That is 32.4, this first measurement, in centimeters. All right, let's do it again. This time I'm at 32.6. This time 32.5. So we'll average that, which should be 0.325 meters, and calculate the wavelength by doubling, and then you can calculate the velocity, okay, with the equation that's given to you there. And of course, after you've done that, you're going to compare the velocity to the given speed of sound, and the speed of sound will depend on things like temperature, the density of the air. So it will vary a little bit, but at sea level, standard temperature pressure, it's given in the back of the lab manual here. And it's going to be 343 meters per second is the standard, so you can compare to that. All right? So we'll see how close we get with that value. All right, next we're going to go to the second part, which is closed-end pipe. Okay, so I'm going to run through this quickly as I can. So we have, again, a 480 hertz and then a 512. So I'm going to do 3 trials of each. Now this is going to be the closed end. Now, based on what we saw earlier in the 2 figures, so figure 4 was showing the closed-ended pipe. So we're going to have the antinode here, or sorry, the node, and the point at which it will reflect off the back. So we're going to have the sound reflecting off and going back out. We're going to look for the antinode, which is the point of maximum amplitude, okay, at the opening of the mouth. That's when we're going to hear it being the loudest. All right, the easiest way I find to do these is to first get a, start with the B, is to get a ballpark idea of the length. Okay, just in case that's hard to hear on the camera. So I know it's going to be somewhere around there. So I'm going to hold this with my other hand and make minor little fine adjustments here. Okay, so now I'm going to hold the 2 pieces together so it doesn't slide, and I'm going to line up my meter stick here, and I'm doing this based on the edge of the cap. Okay, I know the cap has a little bit of thickness here, so I'm not going with the very end of the cap here. I don't want to go off this end. I'm actually going to start here because I know the cap thickness, so my node is going to be somewhere just inside this cap here. So I'm using my knowledge of that to go off this sort of rounded edge, if you can see that potentially on the camera. I'm going to go over and see my total length here is 55.5. Okay, let's do it a second time. $55.6. This time I'm 55.3. Okay, 0.553. So find the average length of that. But in this case, our configuration is going to be 3/4. And they tell you this in the lab manual. If you look in step 2, they talk about that length is 3/4 of a wavelength. So you're going to make sure that you multiply by 4/3 to get your correct length there. All right, so once you have the wavelength, after you've averaged those lengths, you'll be able to calculate your velocity, compare it to the 343 meter per second number again. All right, so let's jump to C, and this will be our last set. Okay, I'm pretty close here. Right there. $51.1. And again, that's in centimeters. Sounds good. Let's call that 51. Final time. Okay, and this looks to be 51.2. Okay, so calculate your velocity and compare it to 343, and then you should be able to do write up a simple lab report. You'll submit that to Canvas. I will share this data sheet with you in Canvas as well. So look for it there, and ask your TAs if you have any questions.